design of transmission line, as we discussed, we have to consider three important points. First one is voltage at the receiving end should not vary too much. It must be within 10% change. Then the losses must be small, and therefore you will get higher efficiency. Basically, you need to get a reduced current. If current is less, losses will be less. And same case for I square R losses. I square R losses related to current. So if current is higher, I square losses will be too much. I square R losses will be too much. And this loss will be in the form of heat. If this heat overheat the conductors, resistance will again increase, losses will again increase. So the losses must be like it should not overheat the conductors. So these are the 3 points you have to consider when you design a transmission line. Okay, before we go for design, we have to talk about what are the transmission line parameters. That is simply equivalent circuit of a transmission line. This we discussed even last class. So there are 3 important parameters: resistance, inductance or inductive reactance, and then capacitive reactance. So these parameters, not like other motors or transformer, it is not concentrated at one point. It is distributed throughout the length. So here we have to use some simplified equivalent circuit to represent a total transmission line. As we see here, this lower part, this diagram is total transmission line is divided into small pieces. For example, 1 kilometer. So each section have a resistance, inductance, and a capacitive reactance. Inductive reactance and resistance will be connected in series. Capacitive reactance will be connected parallel. Many such units are connected together. But if you have such a long diagram, it is difficult to solve or find parameters. So what we do is we will simplify it by considering the total resistance, total inductive reactance, and total capacitive reactance. And as an example, like we will make a shape like this: X and R in series and capacitor will be parallel. So to decide this parameter, transmission lines are divided into 3 categories: short line, medium line, and long line. Short line, less than 80 kilometer, from 80 to 240 will be medium line, and more than 240 kilometer will be long line. So short transmission line, here since the length is less, effect of the capacitance and leakage will be less. So we can neglect it. So we will consider only a series resistance and a inductive reactance. No parallel capacitance. Capacitance will come into effect if the length is more. Then medium transmission line, there is sufficient length. It is more than 80, less than 240 kilometer. So you have to consider capacitance. And where we will connect the capacitance. Based on that, we have 2 different main models. One is T model and other is pi model. In T model, capacitor, the whole capacitive reactance will be connected in the middle, and the resistance and inductance will be divided into half. Half will be connected before the capacitance and the remaining half will be connected after the capacitance. For the pi model, what we do is, this is the most commonly used technique: resistance and inductance will be connected completely, and the capacitance will be divided into half, so that half of the capacitance will be in the sending end and the remaining half capacitance will be in the receiving end. And there is even more accurate method if you combine these 2 together. So there will be resistance and inductance will be connected into half, divided into half, and capacitance will be divided into 3 pieces. First one will come in the sending end, another piece in the middle, and the last third part will be in the receiving end. So these are the methods of medium transmission line. So most commonly is T method and pi method. Again, pi is the most commonly used technique. Then comes long transmission line. Here accuracy is very important, so you cannot go for simplified. as we see in the first figure, you have to consider each and every part of line, and it will be a complicated equation. And here, one more important thing is you have to even consider this leakage reactance. This is happening through the leakage through the resistance, sorry, the insulators. So that also, to be accurate, you have to consider all the parameters, and a big equation and big complex solution method must be used to solve this transmission line. Now, coming to the standards and data sheets which we studied in previous lecture. The design of transmission line is done with the help of some set of data sheets. What we studied in the previous lecture was a data sheet which is used for selection of voltage. Selection of voltage is important. Equally important is some data sheets which is related to the parameters of transmission line: resistance, inductance, and capacitance. Inductance and capacitance normally which we use for a three-phase 60 Hz line is almost some constant values. If it is an overhead line, the inductive reactance per kilometer, remember it is for per kilometer 0.5 ohm. And if it is an underground cable, XL, not L, XL value is 0.1 ohm per kilometer. This is the standard value which we use. IEEE standard or ANSI standard. And for capacitive reactance, not capacitor, capacitive reactance for an overhead line is 300 kilo ohm, and underground cable it is 3000 ohm. Capacitance will be more. You remember equation for XC? XC is 1 over 2 pi FC. So if capacitance is more, XC will be less. So less capacitive reactance will be there for underground cables. It is simple for inductive reactance and capacitive reactance. But coming to this resistance of the cable or the transmission line, we are considering anyway the overhead lines. The resistance depends on many other parameters. Resistance mainly depend on the wire size. We know the equation R is equal to rho L over A. Based on the conductor used, if you use copper, we study about different types of conductors. If you use copper, if you use ACSR, normally we use ACSR, so this will be the most common type. And based on the wire thickness, the resistance will change. Also length, but we are talking about resistance per kilometer. So if it is a 10 wire gauge, its resistance per kilometer will be, for a ACSR conductor, will be 6.7 ohm. For wire gauge, as it changes, the ACSR conductor, the resistance will be changing, and as the diameter increases, you can see resistance decreases. These are the standard values. Similarly, wire gauge is given also. Each wire gauge, this is the cross-sectional area in millimeter square. If wire dimension can be specified in two different ways, either in wire gauge size or it can be in the millimeter square. So if it is in millimeter square, you have to use this table. So how we will use the table is, we will use, there is a current capacity given here. This up to 70 ampere capacity if it is copper, and if it is ACSR conductor, all the below 140 ampere, 140 ampere, you can use any of these wires. If it is more than 140 and less than 200, you can use wire gauge 1. So based on the current, we will decide the wire gauge. Based on that wire gauge, you will calculate the resistance. So these all are connected together, and to get current, you must know voltage. So first, the table which we studied before, voltage table, that is important. From that, we will get voltage. Using that voltage, we will calculate current. You remember we did a numerical example. First calculated voltage, then you calculated current. Now that current will come here. If that current is, for example, 200, you have to select wire gauge 1. And what will be the resistance of that? If it is a copper, its resistance will be 0.5 ohm per kilometer, or if it is ACSR conductor, its resistance will be 0.9 ohm per kilometer. So like this, we have to calculate resistance. And voltage, already this is the standard where we calculate voltage. Now we are going to a numerical example. Here we are going to find the transmission line parameters. Also, we are going to draw the complete equivalent circuit. Here voltage is given directly. You don't need to calculate voltage. So a 3-phase 230 kilovolt transmission line having length 50 kilometer is composed of 3 ACSR conductors having cross section is 1000 kc mil. You see this here, 1000 kc mil. So wire gauge size, everything is given directly here. You don't need to calculate anything. Wire gauge size is given, voltage is given, and you have to calculate the transmission line parameters. This I will show you how to do it. Are you able to see my screen? Hello?
Yes.
Okay.
Yes.
So we will take this question, that is it is a 230 kilovolt transmission line having length 50 kilometer. So the length is given as 50 kilometer. This is the first point. So you have to write L equal to 50 kilometer. Now voltage. What is voltage? Voltage is 230 kilovolt. What is given next? ACSR conductor size is 100 kc mil. So this 100 kc mil, now we have to go back to this data sheet. In this data sheet, 1000, no, not 100, 1000 kc mil, we are using ACSR conductor. What is the resistance? Resistance per kilometer. Small r is 0.065. 0.065. So small r is 0.065. This is small r. So what will be capital R? What will be the resistance? 0.65, sorry, 0.65 multiply with 50 kilometer. It's not clear. 0.065 multiply with 50. 0.065, which you see here, is for per kilometer. So for 50 kilometer, you have to multiply it with 50. So what will be the value? You will get value as 3.25 ohm. ohm. Now comes the inductance. Inductance is a constant, 0.5 for overhead line. So x small xl is 0.5 and small xc is 300,000. So xl is 0.5, xc is 300,000. These are small values. Coming to, so already we got R equal to 3.25 ohm. Now XL, how much will be XL? 0.5 multiply with 50 is 25 ohm. And what will be XC? XC is 300,000, not multiply with 50, because XC is 1 over 2 pi FC. So here, as the length increases, capacitance will increase. That means the XC will decrease. What you have to do is divide by 50. If you divide by 50, the value you will get will be how much? 300,000 divided by 50 is 6,000, right? 6,000. Oh. So you got R, XL, XC. This is our first part of the question. Determine the transmission line parameters. Then comes the next part. That is, draw the completed equivalent circuit. You remember equivalent circuit? I told you. Okay, these are the values. Don't forget 3.25, 25, and 60. Sorry, 6,000. When you draw equivalent circuit, this is 50 kilometer. So you need, or we will draw a pi model. R, inductor. Then you need 2 capacitors here. This is the pi model. R value already we got. How much? 3.25. That is R. XL value was how much? XL value was 25. Now coming to XC. XC, we have to divide here and here. Here you need a part of XC, here a part of XC. Here we are dividing half of C. That means XC will be double. You have to double XC. When you become half, XC will be double. So here actually 2 XC will come. 6,000 multiply with 2, so this will be 12,000 ohm, and here also it will be 12,000 ohm. Equivalent circuit, resistance, inductance, capacitance, all came. Now comes, you need to write what is the voltage. Voltage is already given. Voltage is 230 kilovolt, but that 230 is a line to line voltage. 230 is a line to line voltage. This 230, if you make a phase voltage, you have to divide it with √3. What you will get if you divide? 230 divided by √3 is 133. So it will be equal to 133 kilovolt per phase voltage. So here you have to write 133 kilovolt, and here how much it will be? 220. See, at the load side it is 220 kilovolt. So I am not calculating. You can write 220 divided by √3. You can write like this also. You can write 220 divided by √3. So if 133, if you forget, if you write 230 divided by √3 also is correct. So finally, your diagram will be like this. Sending end voltage is 130 kilovolt. Resistance is 3.25 ohm. Then XL is 25 ohm. Then XC divided into 2 pieces. Actually, it was 6,000. So when you make half, actually it is not half. XC case, it will be just opposite of other. So it's of 6,000, it will be 12,000 in this side and 12,000 the other side. So 12,000 and 12,000. So like this, there will be a equivalent circuit. Now you designed a transmission line. This is what is meant by design of a transmission line.